Hello everyone. Hi. So good evening. So today we will be starting our live session. Yeah. So today is week 11. So give me a second. So we'll be starting very soon. So let me share my screen. Thanks Diksha for joining. Okay, so today's topic is about first we will be saying some what how can we calculate the performance of demand paging, which is how to calculate the effective access time. Then we'll be saying the demand paging optimization. We'll be saying the demand paging in mobile system, copy on write. Why there is a need of page replacement and some page replacement algorithms and page replacement algorithm like fast in fast order algorithm. Then what is the number of frames versus why there is a trade-off between number of frames versus number of page faults. And then there is a abilities anomaly for FIFO algorithm, then optimal page replacement algorithm, LRU, which is least recently used algorithm, uh, some stack algorithm, and then also we'll be seeing the second chance page replacement algorithm, and how can we allocate the frame and thrashing, and there is what's the difference between demand paging and thrashing, how these both works, and also the page fault frequency, and basically this based on this and also if there's a page table, then there comes inverted page table, then input output interlock and page locking. So this kind of thing will be seeing. So this is the first question for our today's lecture. So you can start by answering the question. Then I will be moving to the another. Okay, so about the first question, which is that select the correct statement or for the FIFO, which is first out page replacement algorithm. So it replaces the page that has been used the most time. It replaces the pages that has been used the least time. It replaces the oldest page in memory. It replaces the page with the lowest frequency of use, or uh, it replaces the pages with the highest frequency of use. Okay, so these are some of the options. Yeah. So why there is a need of page replacement basically? Okay, so we know that what does it mean by so before that we need to know something called, so it all start from threshing. Okay, so, like in what why there is a need of what is the importance of frame allocation and page replacement? Okay, so we know that in virtual memory we have two things, that one is frame allocation and one is page replacement. Okay, so now one term call is coming, that is threshing. Threshing is for if for every instruction there is a page fall. Page fall means, so you want a page, but you want a frame basically, but it is not present in the main memory. So what you need to do, you need to go back to the your hard disk, you need to load it and then come back. Okay, so if this happen for every instruction, okay, then it is called threshing, right? Then the execution, so so why this is not it's not it's not a expected thing, because if this is the case, then your execution time is going to increase exponentially. So that's why it's called the threshing. Okay, now what are the cases what we do to prevent this? We do frame allocation. Okay, so there are three cases of frame allocation. So you can do equal allocation, you can do weighted allocation, and you can do dynamic allocation. Okay, so suppose there are three process. Okay, so each process containing some number of pages. So you know that P1 contains 10 page, P2 contains 100 page, and P3 contains 300 pages. Okay, then what is the number of frames? You know the number of frames is fixed, so it is 30. Then you will give 10 frames for each process. So you know this. So now your maximum one is 300, so you will give 10 frame for each process, right? Now what is weighted allocation? So you will give more frames to the process which it need more according to the requirement. So P1 need P1 need 20 pages, P2 has 30 pages, and P3 has 50 pages. So and number of frames is equal to 10. Hello, is not it clear? Give me a second. Is it clear now? Is it fine now? Hi, is it fine now? Can you confirm once? Okay, okay, okay. So here you have 10 frames for now you have 10 frames altogether. Okay. Now so you will give P1 will get 20 by 100 into 100 is equal to 2 frame. Okay. How I am giving the frame? So P2 will get, so based on their weight, so total need is 100. The total, if you do total, that is 100. So you are giving the weights. Okay, so it will be 3 frame, and for P3 it will be 5 frame. Okay, so this is the kind of thing. This is a static method. Okay, but there is also a dynamic allocation. Okay, so we will be seeing the dynamic allocation first. Okay, so there are some page replacement algorithm. Okay, and okay, so I am trying to giving you a overview basically what is happening here. Okay, so if you have a page replacement algorithm, so you have a there they are of two kinds. One is local, one is global. Okay, so what does it mean by local and global? Okay, so if you have a process like this, okay, so from this to here it is P1, from here to here it is P2. So this is your main memory. I can write it here. This is your main memory, and it is written like this, right? So from these are the P1 process, and this is the process for P2. Okay, now local page replacement algorithm not only replace the pages from where it initially loaded, so it will work on P1 only. So it will replace the pages from P1 only. Okay, so are you getting my point? So if you have a local page replacement algorithm, then they will work from this area only. Okay, they will not touch this area. Okay, so this is something practically used. uh, so okay, now one term comes into our picture, that is yeah, that is called demand paging. So what is demand paging? So we will not load any page until it is asked. Okay, okay, is that we assume that we have not loaded any process in main memory. Okay, so it is an assumption that we have not we have not loaded any process into main memory at initial at the initial point. Is that at the starting of the program? So when you are starting of the program, okay, you have not loaded anything into this main memory. Okay, so you will be loading when there is a need. Okay, now the opposite of demand paging is pre-paging. So you have a concept, it is given, so you can, if you see the lecture notes from your NPTEL class, so you can see that other consider, so at the very bottom of your slides, you can see that other consideration are pre-paging. So what is the concept of pre-paging? So pre-paging is basically, so you are loading all of your programs into main memory when it is initialized. Okay, so you are basically loading each and everything beforehand, not looking into the not considering the requirement. Okay, so this is the pre-paging. Okay, now there are some reference string. So reference string is when CPU is going to generate some addresses in order to execute a process. Okay, so this term is important because I think this was not mentioned in our course. So that's why I am trying to add this reference string, because how you will get to know that which process need to be allocated, reallocated, or which process need to be loaded in this frame, or sorry, which page is need to be loaded in this frame, something like this. How will get this? So referring string is nothing but the page number. Okay. uh, so CPU will generate this reference string, or the uh, if my voice is low, what can I do? It is not clear yet. Okay, okay, so maybe I need to use my headphones. Yeah. So so I was talking about the pre-paging, which is needed because of the which is the opposite thing of the demand paging. And one thing is reference string. So reference string is when CPU is going to generate some addresses in order to execute a process. So CPU need this sequence of page in a particular order. So reference string is basically nothing but your page numbers. Okay. So now first algorithm comes, that is optimal page replacement algorithm. So what is the optimal page replacement algorithm? So in this algorithm, pages are used for the longest duration of time in future. So look at the future to decide for the page replacement. But you know that so in this optimal, so basically you will be uh, looking into the future. Okay. And you know that also this is in our curriculum, but this is not practically possible. Okay. So this optimal page replacement is not practically possible because you have to look into the future to see that which which page would need for the longest duration of time. Okay. Now second one is least recently used, or it is called LRU. Okay. So LRU is a practically possible. So uh, so so suppose you have, so this is your page number 4716. So from here to here, so this is right. So 6 is the, so you are now at page number 6, time t. Okay, so this is time t minus 1. So this is the, so this is the most recently used. Got it? Okay, so this is the most recently used, and this is the least recently used. Got it? So this is t. So you are now here in this point, in this position, t minus 1, t minus 2, t minus 3. So the last one will be the least recently used, right? Now what is the now our third algorithm comes, that is FIFO, fast in fast out. Okay, what does it say? That the, so this is the simplest one. Okay, so the simplest page replacement algorithm maintains a queue for this. So the oldest page is in the front of the queue. Okay, so uh, so whenever you will do this, so this you have 3 frames, right? And you have like 4 7 6 1 2. So you will maintain a queue. So suppose first 4 comes, right? So 4 here, 7 here, 6 here. Okay, you are going from this side to this side. 4 7 6, 4 7 6. Okay, now you have 1. So how you will replace it? So this is your queue. So it came first, 4 came first. So q is from, this is in, this is out. Okay, so 4 will be out, so 4 will be, and 1 will come. Then 7 will be out and 2 will come. Got it? So this is the FIFO algorithm. So which one is the best page replacement algorithm? So optimal page replacement is the best. Okay. So and one thing need to remember, I remember it, that number of page fault is equal to numbers. Okay. So how I decide it, right? So in this program, how many page fault are there? So you can see that first, whenever we started from 4, so at 4 the frame was empty, 7 frame was empty, 6 frame was empty, but so yeah. So the question is about like, consider the computer system executing a process of size 20 KB. So in the main memory with the following page reference string 0, so I can write it here, 0 1 2 3 0 1 4 0 1 2 3 4. The size of each page is 4 KB. Compute the number of, so this information is really not required. Okay, and compute the number of page faults for the first FIFO page replacement algorithm for 3 and 4 frames. Okay, so let's see, let's solve it. Okay, so first do it with 3 pages. Okay, now I have 0 page fault, 1 page fault, 2 page fault, now 3 comes. So I have to maintain a queue, 0 1 2, now 3 comes. So I will so 3 comes, I remove 0, write 3 here. Now 0 comes, now I will remove 1, write 0. Okay, now 1 comes, now I remove 2, write 1 here. Okay, now 4 comes, so remove 3, write 4 here. Now 0 comes, 0 is not a page fault. Now 1 comes, 1 is not a page fault. 2 comes, 2 is a page fault. 0 2, now 3 is a page fault. 1 go, 3 comes, 3 comes, 4 is not a page fault. So how many page fault is here? So total 9. Okay, with 3 frames. And if there are 4 frames, there are 4 frames. Okay, so I have to maintain a queue. 0 comes, page fault 1 2 3, 1 2 3. Okay, here it is done. Now 0 comes, that it is not a page fault. 1 comes, it is not a page fault. 4 comes, now 0 will be replaced, 4 will come here. Now 0 comes, 1 will be 1 will be replaced and 0 will come. 1 2 will be replaced, 1 will come. 2 3 will replace, 2 will come. 3 4 will replace, 2 will come. 4 0 will replace, 4 will come. So page fault is equal to 10. Okay, see here that number of frames is more here. Okay, here you have 3 frames, but here you have 4 frames. You have more opportunity to store more data. Okay, but number of page fault is high in case of these 4 frames. So this is called Bilet's anomaly. Okay, so this happens in first out. Got it? Yeah. So basically, a page fall occurs when a page is not found in the memory. We know it. So and it needs to be loaded from the disk if a page fall occurs, and all memory frames have been already allocated. The replacement of a page in memory is required on the request of a new page. So this is referred to as demand paging. So generally, on increasing the number of frames to a process virtual memory, in the virtual memory, its execution become faster as less number of page fall occur. But sometimes the reverse also happens, is that more number of page fall occur when more frames are allocated to a process. The most unexpected result is termed as the Biledis anomaly. Okay, so in which algorithms you can see Biledis anomaly? So Biledis anomaly can be seen in FIFO. You cannot see in LRU or optimal page replacement. Okay. Second chance. See, random page replacement. Okay. So this is a important information. Oh, great. Now can you tell me the answer of this? Okay, so the correct statement for the optimal page replacement algorithm, that it has highest page fall for a fixed number of frames among. No, this is not true. Biledis anomaly is occur when FIFO or second chance and random. It has lowest page fall for a fixed number of frames among all the page replacement algorithms. So C is the correct answer. Okay. Can you work on this example? 8, right? Diksha, 8 is not the right answer. Can you please try it once again? Okay, so let me solve this for you. Okay. So we are using the least recently used. Okay. So what are the pages we have? So we have 365 065 0161, right? So yeah. So how many frames we have? We have three frames. This information is not required. This information is also not required. Okay. So I am at 3. I write 3 6 6 5 5. Now I have 0, and so at 0 3 is the least recently used. Remove 3 and make it 6 here. 6 6 is fine. 5 5 is present. 0 0 is also present. Now comes 1. So which is the least recently used between 0 6 5? 6 is the least recently used. So I will remove 6 and make it 1. Now 6. So which is the least recently used between 5 0 1 5? So I'll make 5 and make it 6. And 1 is present. So how many page fault? Is equal to 6. Because total, you can see that total 6 numbers are written. Right? So this is how we'll be solving. Yeah. Now can you solve this one? Okay. So here that which of the following statement is true. So we have in global page replacement algorithm, a process cannot control its own page fall rate. Okay, this is not true. And in global page replacement algorithm, a process control its own page fall rate. So there is no connection in using the page fall rate. So this is the truth that global page replacement algorithms suffer from thrashing. Okay. Now, okay, I have a question for you. Then, okay, the question is: a system uses FIFO page replacement policy, okay, and it has 4 page frames with no pages loaded initially. Okay, okay, so frames are empty. Now the system first access to 100 distinct pages in some order, okay, and then access the same 100 pages but in reverse order, okay. How many page fault will occur? Okay, are you getting my point? So you have sorry, you have uh, you have you have 3 frames, okay. Oh, 4 page frames initially. Sorry, not 3. It is 4. Okay, it is 4 page frames. So you are accessing like 1, 2, 3, 4 dot 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 96, 97, 98, 99, 100. Okay, then you are accessing in reverse order 100, 99, 97 to 2, 1 like this. Okay, now tell me that how many page fault should occur here. Write the numerical answer in chat box. Okay, so you are saying 200 page faults. Yes. Uh, yes. See that. So you will be meant. So you are using FIFO. So in FIFO, like 1, 2, 3, 4, like this come. Okay. Now they 96. So consider the situation when this number comes. 96, 97, 98, 99, 100, 99, 98. Okay, so consider this number only. Sorry, this is not your so this is not your queue. So I'll be maintaining a queue where I have 96, 97, 98, 99, 100. So this is my queue. Okay, now what will happen that 96, 97, 98. Oh, sorry, so I should start from 97, then my things will 97, 98, 99, 100. Okay, right? Now what happens that if you have in this situation you already have 100 page faults. You are here, you have done this, you are here 99. So what happens that you can see that, oh sorry, we have a 100 here also. So this 100 is not a page fault because 100 is page. This 99 is not a page fault. This 98 is not a page fault. 97 also not a page fault. Okay. This 4 is not a page fault. Then 96 will come. 96 so 97 will go and 96 will come up here. Okay. So there are total 200 minus 4 is equal to 196 page faults. Are you getting? So if you have understood, then tell it in the chat box, or if you didn't understood it, then tell me. I will say it again. Okay, is it fine? Okay, then we can move on to the next question. Okay, I should explain again. Yeah, sure. Yeah, this is an interesting one. So, so I have a frame. How many number of frame? 4 page. 1, 2, 3, 4. Okay. So now I will maintain a queue. Okay. So first one will come, one will sit here. 2 will come, 2 will sit here. 3 will come, 3 will sit here. 4 will come, 4 will sit here. Now 5 will come, 1 go, 5 come. 2 go, 6 come. Okay. 3 go, 7 come. Okay. 4 go, 8 come. Okay, so this is how my thing will continue, and these all are page faults. So up to 8, up to number 8, I have 8 page faults, right? Is it correct? Okay, so up to number 8, so suppose here it is 8, there are 8 page fault. Okay, okay, so this is the current situation. Now what I want to do, like I so I want to say that now I have 96 go. Okay, so so maybe you can see here, like we have 97, 98, 19, 99. So this is the current situation. So up to number 100, how many page fall we got? Because we have 96 here. Okay, we cut it 96 and put it 97 here. Okay, so we have 95 here, put it 95 and 98 here, right? So this is how. So up to 100 we have 100 page faults, right? Now what happens that now, so I am currently at this position 100. Okay, now I will be moving my position to 100. Okay, but see here that this, so in my queue also 97, 98, 99, 100. Okay, so you can see that 100 is already present. 100 is already present. So this is not a page fault. So I am saying that this is not a page fault. Now I come to 99. 99 is present, so this is not a page fault. 97, 98 is also here. 98, 99, 97. Okay, 97 is not also a page fault. 97, 98 is here, so it is not a page fault. 97 here, so it is not a page fault. Okay, so now what come? 96 come. You can see that 96 is not here. So 97 was the out, and this was the in. So 97 was the first thing to get out. So 97 will be replaced and 96 will come. So I have found that these four pages has not replaced, right? So but again after 97, 96 will come, 98 will be replaced and 96 will come. So 95 will come. Okay, sorry, 95 will come, then 99, 94 will come, 100, 93 will come, like this. Okay, because we are going to the reverse order. So these four pages is not replaced. These four pages, which is 90, 97, 98, 99, 100. So total pages are 200, because 100 upwards, then 100 reverse. So 200. So but in between we have 4 pages which was present in the frames, for which the page fault did not occur. So total 196 page faults. Fine? Is it fine now? Can you write in the chat box if it is fine for you? Yeah. Fine. So now the question is, yeah, this is the question. Next. Okay, you are saying C is the correct answer. So thrashing occurs when the memory is overwhelmed by excessive paging or so. Yes, C is the correct answer. Okay, so this is a new concept kind of. So this is saying that consider a working set window. Okay. So there is a so nearest future is the base is the close approximation of the recent past. Okay, so working set algorithm is the in locality of reference, a particular memory location is referenced then it may refer in the same location in the near future. Okay, are you getting my point? Like, so in Zomato, like food delivery app or something like this, so so it assumes that if you have ordered biryani recently, so you will be ordering it very soon again. Got it? So this is the same thing it is using. So in locality of reference, a particular memory location is referenced, then it may refer in the same location in future. So here locality is the set of pages that are actively used together. Okay. So locality means, so you have the frames, so you have used certain pages recently, so you will be using the same set of page number very soon. Okay, so in working set algorithm, working set window tells how many pages references are there in a locality. Okay, so in working set window there is a call that working set window. This one, this working set window tells how many page references are there in a locality. Okay, right? So if all pages references are there in memory, then there is no page fault, else page fault occurs. So when a page process execute, it moves from one locality to another locality. Okay, so consider this, like 2 3 5 2 4 3 6 7 1 5 5 1 2 3 4. I am just writing this one. So what is the, our question is, what is the working set at the 13th time unit within the window? Yeah, we'll find it. We'll find it. So you have 10 memory references. Okay. So basically, how you will do this? So first, you will be using these four. Okay. Should I write? First, this will be used. Oh, sorry. So time instance at time instance 1, it is this is t1, t2, t3, t4. So from up to time instance, yeah. The question asks for the working set at the 13th time unit. The meaning we need to consider the page references made between from 5 to 13. So because we have 10 window size. Okay. So this is 4, 3, 6, 7, T5, T6, T7, T8, T9, this is T10, T11, T12, T13. So the answer will be the last one. So this one is the answer. Yeah, so E will be the correct answer, okay? Right? So this is the last question for today's class. Okay. So for this the optimal page is future memory reference. So this is the correct answer. Okay. So fine. So this was the all setup question. So thank you everyone.